Hi, I'm Harry Powell. I'm Head of Industry Solutions at TigerGraph, I guess as it says in the caption below. I am really looking forward to telling you over the next 25 minutes, half an hour, about some stuff we've been doing around graph machine learning and the amazing results that we've been getting, and hopefully how you can benefit from it too in your own data science work. I'll kind of cover a little bit about what graphs are and about some intuition behind why graphs are interesting and important. And then we'll go into talking about machine learning, kind of classic machine learning, graph neural networks, and a new product from TigerGraph called Machine Learning Workbench, which makes it really, really easy to do cutting edge graph neural networks on on your sort of standard kit with your standard teams and all of that, right? So that's the program for where we're going, and I look forward to telling you about it. Okay, so TigerGraph is a platform for machine learning and analytics on connected data, and we'll go on in a second to what connected data is. I think our particular USP is that we're the only scalable platform for doing that. So if you want to be doing analytics and machine learning on connected data, either on large data sets, or if you want to be running algorithms and kind of compute heavy machine learning, you've kind of got to be using a platform like ours. And I suppose about TigerGraph, well, we've been around for 12 years, I think. We've been in the market for the last 5. Up until then, we were in stealth, developing the engine. We're based in Redwood City, California. Got a number of large clients, but we're always looking for more. And one of the things I guess I can tell you is that JP Morgan really like us. They gave us their inducted us into their Hall of Innovation just a year ago. Which is pretty good accolade for us, and we were pretty pleased about it. Okay, so let's tell you a little bit about graphs. Okay, so here's a picture I quite often use. What is a graph database? Why is this interesting, right? Well, the picture on the left is a picture of a bunch of flowers, and the picture on the right is kind of how you would represent a bunch of flowers if you're interested in kind of normalized form tabular databases. You'd kind of pick apart all the flowers and the leaves, and you'd put them into kind of tables, right? So you'd have all the leaves in one place, all the flowers in another, all the seeds in another. And that's a pretty efficient way of storing data, but somehow you lose the sense of what that bunch of flowers is on the left, right? A graph database tries to store data and is built from the ground up to store data in a way that kind of keeps the relationships between your data, in a way keeping like the bunch of flowers. You can figure out what the bunch of flowers is because it doesn't have to break it up into bits, right? And in TigerGraph, the relationships between the data points, just as the relationships between the leaves and the petals and the flowers, the relationships between those data points are just as important as the data points themselves. So you have a platform for analyzing not just the data points, the kind of conventional records of your data, but doing the same kind of analysis on the relationships between them, able to run algorithms on the relationships, not just the data points themselves, right? Relationships are first-class citizens in a graph database. So when I talk about a graph, what do I mean? So I've talked about this bunch of flowers and the way that you represent data from the real world, right? And trying to keep the relationships between things. How might we represent data that's not in tables, right? And we use this thing called a graph. Now, a graph in this sense is not a chart, a plot, or a diagram. It's a network, right? So when we say graph, it's a mathematical term for a network. It's kind of an unhelpful term, I guess. But when I say graph, hear network, and you'll be in the right kind of place. This is a network, right? It's a kind of a small network. It's about people who maybe have accounts at banks, who live in certain places, and who use certain devices for interacting with those banks, right? And you can think of the graph as a combination of nodes, which are these circles. They're the entities involved, and in this sense, and also what we call edges, which are the dotted lines between them. These are the relationships between them. So David, for example, uses a MacBook. He lives in Los Angeles. He banks with Capital One. Lisa, who's his sibling, I guess it's his sister. I don't know where she lives, but we know that she uses a smartwatch and banks with JP Morgan Chase. Okay. Oh, no, she does. She lives in San Francisco. That's where she lives. So we're coding a whole load of information, not in tables here, but in nodes and edges, things and the way those things relate between them. That turns out to be a really, really powerful way of storing and thinking about information. And TigerGraph, like the other graph databases, it's built from the ground up to think about data in that way, right? So it doesn't have tables and lists in the background, right? It's not a view on a conventional database. It's actually it's a bunch of memory pointers and hash maps that allow you to directly move from one node to another along the edges, right? That's called a traversal or a hop. You can traverse from one node to another. And so if you want to run an algorithm which involves moving around from one place to another, or if you want to from one place to another, from Lisa to JP Morgan Chase to John to Palm Springs to Jim to iPad, whatever it is on this, you need to be able to do that using a graph database, because if you don't and you use a normal database in the background, then every one of those hops is a table join. And if you've got, I don't know, 10 million records in the table, you're going to be really burning compute a lot to do that. Okay, so we got a graph. We've talked a bit about a graph. Maybe I've gone on about it too long, but this is how you might encode the world. And you've got to understand that this is suddenly a much richer environment. You've got something there that you never had before, explicitly encoded relationships. So what might we use those relationships for? Okay, I'm going to sort of stick largely in a financial services background environment here. I guess it's New York, data science salon, New York. So I'm hoping some of you guys are data science people from financial services, but most of what I'm talking about here is much more broadly applicable. Okay, so relationships. What might we be able to use the relationships between data to do? Well, here's a viz about data integration. So you've got a couple of tables, accounts here and mortgages, and you want to be able to bring that data together into a single table, link the two. Maybe they come out of two different systems. Maybe those systems are in two different entities. Maybe there are no unique identifiers that allow you to match between people who live in addresses and do certain things on certain dates in one system, and people addresses and dates in another system, right? How are you going to match those things together? This is a classic data engineering problem. It's the starting point of a lot of data science, right? It's trying to connect information together, and often it doesn't cooperate, right? So we can use the relationships between things. In other words, how people relate to where they live and the dates, to do a version of entity resolution called graph entity resolution, which allows you to connect information together, connect tables together, even when you have no unique identifiers, right? It does it by turning the combinatorial problem on its head, right? So if you wanted to match up every record with every field in the best possible way between two tables, particularly if you didn't know which column related to which, right? Which is quite often the case, right? If you might have multiple date columns or multiple address columns or that kind of stuff, then you've got a massive combinatorial problem, right? Which you have to fight with logic. But with a graph, and I don't have time to go into it now, you can use the relationships between things to turn it on its head and make the combinatorial problem your friend rather than your enemy. And it allows you to combine information much more efficiently than trying to do it through logic on tables. So that's the first thing. Relationships between things can help you combine information or make sense of information in order to combine it, even when there are not, even when you don't have all the information you might like to. It's the first way you might use relationships. Secondly, and here's a fraud example, so a banking fraud example, another visualization here. You've got this problem here where you might well think that if you're trying to combat fraud, you want to be thinking about the relationships between people, not just their behavior, the kind of or what you know about them, right? Which is a conventional machine learning approach. You say, well, yeah, let's take that, but let's also think about the relationships between people in my system, because the intuition might be that the closer an account is to an account suspected of fraud, the more likely it is itself of committing fraud, right? So if I happen to share a mobile phone number with someone who's a suspected fraudster, it's quite likely that I'm a suspected fraudster, right? Or a fraudster. But it can go much more deep than that, right? Maybe there's 2 or 3 steps, 4 steps, 5 steps between us. I share a house with someone who shares a mobile phone with a business colleague who has a fraudulent account. Whatever it is, there can be a number of steps, and of course, tracing through all those steps is possible with a graph database in a way that it isn't really possible to any large degree with table joins, right? You kind of run out of compute power pretty quickly. But what's really interesting about the relationships in fraud is that you can characterize them using graph algorithms, right? You can characterize the graphiness, the connectedness of data, and a graph database is really good at doing that, right? Running algorithms over graphs and coming up with measures by which you can simplify the problem. So maybe we're interested in this fraud case where the person in the middle, 411473, I think, is that the number? It's pretty small for me, right? It's pretty difficult to see. The blue circle in the middle, the blue node, is maybe connected over 6 degrees of separation, maybe connected to thousands, tens of thousands, hundreds of thousands of other people, right? And of those hundreds of thousands of other people, the graph algorithm has identified and filtered out the 3 most suspicious people, right? It's done that by a number of different ways. It's run a page rank over them. It's worked out the number of shortest paths between them, and it's displayed it in a particular way. So here, the thickness of the connection between the orange suspected fraud nodes and the blue node of interest. The thickness relates to how many steps they are apart, for example, and the size of the orange node is to do with their centrality, right? So it's a way of filtering out of all the hundreds of thousands, maybe millions of potential candidates for linking them together, which ones are the most important, right? And a graph database is really great at using the relationships between people to do that. Again, it's not quite fraud; it's financial crime, anti-money laundering. You can with your graph, say, of transactions of money flowing around a bank, for example. You can think about circular transactions, circular payments, right? Which this is where a money launderer might send large numbers of transactions from one account to another, may split them up into smaller amounts, but ultimately the money comes back to the same place, right? And it's pretty hard to follow these things, particularly with table data, but even with graphs, it can be very hard to do it manually. But a graph database is able to run algorithms, again, which can identify these circular payments and see where these loops interact, and what the core accounts, the key accounts are in those, in order to monitor them. Again, these algorithms are pretty efficient in graph databases. And what they're doing here is using the relationships. And here, the particular relationship is the payment, right? The edge between the nodes is effectively the transaction that says one node pays a certain amount to another node. That's a flow of data. A flow of data, yes, it's called a flow of money from one to another, right? So again, we're using relationships, we're using algorithms that run on, or analytics that run on those relationships, much more on the relationships than on the content of the nodes, right? To show us things we couldn't otherwise see and surface them through a visualization. And finally, this is probably a pretty busy slide for you, but this is kind of at the cutting edge of where we are. These are models, high dimensional models for equity demand, using graph neural networks that we'll talk about at the end. But this again is thinking about how does one thing relate to another. And when I learn about the price, say the price of Procter and Gamble stock, what do I learn about the rest of my portfolio, or the rest of the market, right? The relationship we're talking about here is one of kind of inferred knowledge, right? So if you look at the middle of this visualization, you can see the Procter and Gamble stock, and And when I learn about Procter and Gamble stock, um, I imagine there's a price change, a significant price change. Well, I'm also learning a bit about the New York Stock Exchange, right? And I'm learning a little bit about what's happening to consumer goods because Procter and Gamble is a consumer goods firm, and Procter and Gamble has a big exposure to China, right? So maybe I'm learning a bit about China's GDP, or maybe the other way around. Maybe China's GDP is in. When I see a change in that, I can see a change in the Procter and Gamble stock, right? Now, quite what that change will be and the weighting of that, well, that's to be discovered. What's really interesting then is if I learn a bit about the New York Stock Exchange, that's just above P&G in the lime green. All the lime greens are stock exchanges in this, right? Then I learn a little bit about other firms that are on the New York Stock Exchange, right? So I learn a little bit about, say, Pfizer and a little bit about General Motors and all the other New York Stock Exchange, right? Each of them will have their own relationship to the New York Stock Exchange, which I guess in some sense is related to its weighting on the exchange, but it won't be exactly that, right? Now, when I learn a bit about General Motors, right, I learn about the automotive sector. When I learn about the automotive sector, I'm learning a little bit about Renault, maybe in France, which is linked to French GDP, maybe a bit about Mercedes in Germany, which also has a has a exposure to China, right? So when I learn about China's GDP, I learn about Procter and Gamble, Mercedes, and whoever else. And again, but when I learn about Mercedes, I also learn about the DAX, which is German stock market, which infers a little bit about what I can learn about SAP and which has an exposure to France. You can see how when I learn about one thing, information diffuses across the entire network, and not just on a two-dimensional sense. I mean, I can only display two dimensions on the screen here, but of course, any one of these nodes, right, could have many dimensions of communication, and each one of them is effectively a learning path where when you learn a little bit about one thing, you learn about another, right? Now, this is an extraordinarily powerful idea, and we'll come on in a second to how you might use that. Okay. So how do you capture these relationships? Well, I've talked a bit about graph algorithms, specific graph algorithms. You can think of as ways of capturing the graphiness or the relationships of the data you have, right? So you've got a particular structure in the data you may have, whatever sector you're in. Maybe it's cash flows between accounts, or maybe it's who knows who in a social network, whatever it is. But you actually want to capture this somehow. You want to be able to write down a number. It's hard to kind of look at a graph and say, what you can learn from that. Well, there are these algorithms there with TigerGraph. They're out of the box, open source, and you can use them. You can tweak them as you like. Shortest path we've talked about. Community detection is effectively a kind of modularity measure. So it's interested in where a community is where there are more links within the community than between that community and other communities. Louvain is the state of the art there, and we've got an implementation of that. PageRank you'll all know about. That's a centrality thing. So it's kind of maybe in flows and anti-money laundering, you're interested in central accounts where that have outsized influence on what's going on in terms of transactions. And then, of course, and we'll come on to this in a second, graph embedding is another way of capturing, in some sense, a vector which represents the graphiness of the information that you have. Either way, if you want to be using these relationships that I've talked about, you want some way of capturing the information, capturing that graphy, relationshipy kind of information. And algorithms are your basic way forward for doing that. In order to run those algorithms, you'll need a graph database to do that, because, as I say, you want to iterate your page rank a whole load of times around your graph, particularly if it's a high dimensional graph with lots of different kinds of links in there. You're kind of going to have to use graph database to get this performance you need out of that. Okay. So how do you then use those? What can we do, right? We've talked about the theory of being able to spot fraudsters or anti-money laundering or predict demand for assets in a financial market, for example. How might you use that? Well, I'm going to talk about two approaches. And the first is this. This is the easiest way to make money in the world right now. Not quite. I'm sure that up until Sam, whatever he was called, bank fraud man, bank Bankman fraud, whatever. He until he came down, like it seemed like it was crypto. Right now, I reckon that this is a pretty good bet. Okay, so what is it? Well, this is what we did with a number of investment banks and retail banks on Wall Street and elsewhere in the United States. This has had massive improvements in their fraud detection, but we use it elsewhere as well. Fraud is an example, but it's a general machine learning improvement approach. For a couple of the larger banks in the States, it's made them $100 million each year, this approach, right? So it's a lot of money. I mean, that's partly because fraud is a huge problem, right? If fraud was no problem, it wouldn't solve much money. But you can use this anywhere with recommendation engines and all sorts of things. Anywhere where you think you might have graphy data which has relationships in it that's not currently used. Now, if you look at the top part of this slide, you've got a classic machine learning pipeline, right? You've got a bunch of data, you have a pipeline, maybe a Spark pipeline. It creates some features. One way or another, those features are put into a machine learning model. You train your model, you test it, you drive some predictions, and you use those predictions to improve your business, right, somehow. Right? And maybe you're targeting in marketing or whatever it is. It's kind of classic pipeline, right? And that machine learning model might be, I don't know, a linear regression or a decision tree or a gradient boosting model of some kind, whatever it is, right? It's kind of classic model. So what we did with these businesses in the States, these banks and some other businesses as well, is we took exactly the same data. So we didn't touch their underlying data, and we connected into their pipeline at some point and restructured their data as a graph. Right. So any graphiness in it, any relationships in it, we explicitly encoded in the graph, and then we basically just ran some out of the box algorithms on it. All the algorithms all the algorithms I've talked about. So shortest path, PageRank, Louvain, that kind of stuff. And we basically encoded we ran the algorithms, got the results, and effectively appended those results to the feature set, right? The existing feature set. So nothing changed except we added a few extra rows to the feature set, and then we used exactly the same model, which was already highly tuned, right? These were very mature models that had kind of reached the limit of their accuracy. That they weren't getting any better. They were spending lots of money on data scientists, but they weren't getting any better. And we immediately gave them a 20% uplift in accuracy in AUCPR, area under the curve precision recall, right? Which is a key metric in this case. 20% uplift, right? That's the thing that drove the $100 million. And so what is this? What's the intuition behind doing this thing? Because it's kind of a bit mindless. I think we kind of discovered it by mistake, or at least it was kind of a first attempt, and it kind of didn't, we just thought it would be like a baseline. It was a massive improvement. Well, effectively, we are adding new information into the model. This is information the model had never seen before. So you give a model a certain amount of information, you can tune it as much as you like. You're never going to get any more prediction out of it, right? Any more power out of that model. But if you add new information, suddenly that existing model has got a whole load more to work with. That's what we've done here. Effectively, by distilling the graphiness or the relationshipness of the data that we had into a few numbers, which we then allowed the model to use for the basis of its for its pattern recognition, we were able to get a whole load more information out. It's really powerful, really exciting, and really easy, right? So it's kind of like easy money. Okay. But this isn't where we end with graph machine learning, because I think the real big picture here is graph neural networks. And this is the bit where I get really excited and I have to control myself a little bit. But I hope you will, being data scientists at a data science salon, be as excited as I am. So we all know about neural networks, particularly deep neural networks, where we have a number of layers, where each layer is fully connected to the layer before it and after it in some kind of classifier, right? And that's your kind of canonical deep layer, multi-layer neural network. Okay, so what you can, how am I going to explain this? Okay. So the big leap forward in deep neural networks was convolutions, really, right? And convolutions were the point where everyone realized that if you added some structure into your neural network, you could allow it to learn much more effectively, right? So in image recognition, what they said was, let's only connect layers together to the extent that pixels are next to each other in the image. That's effectively what the convolutions did, right? It made sure that it reduced the number of connections between each layer on the basis of an understanding of the world, right? Which is that while an image, an 8x8, for example, imagine a very simple 8x8 image was a vector of 64 numbers, right? If it was black and white, numbers say between 0 and 255. In fact, these pixels had position, right, which wasn't really encoded on that vector, right? Just in the same way as the relationships aren't really encoded in a table. Now, that allowed image recognition to take a massive leap forward. And similarly, graph neural networks do the same thing, because what they say is only allow connections between the layers where there are connections in your graph, right? Where there are connections in the real world that you have encoded through your graph, right? So if going back to our example of price prediction, right? So Procter and Gamble and Pfizer, right, are connected to each other, but only through the fact, right, that they're both quoted on the New York Stock Exchange, right? Pfizer is maybe connected to AstraZeneca through the fact that they're both pharmaceuticals firms, right? Right? You can only get the information only flows, the demand signals only flow from one stock to another through the connections that you define because you understand the universe in which they really exist. Okay. So in the same way as convolutions restrict the model, so does your graph, right? And by restricting the model, we remove some of these connections, and that makes it easier for the model to resolve what's going on, right? Because if you think that a neural network is sort of working out two things at once, it's sort of working out how the world is connected, right? Which connections have a weight that's high and which connections have a weight that's low. In other words, which connections are strong and which ones are weak, right? It has to do that at the same time. It has to kind of calibrate a prediction out of the end. I know they're sort of the same thing. What we do here is by restricting it, we help the machine learning model run. And as a result, you get a much, much better result. Okay. Now, this is kind of cutting edge stuff, right? Amazon does its forecasting on its marketplace using the similar thing. You can see here the majority of this diagram here. You can see the paper quote at the bottom. It's a graph neural network. There's an LSTM below as well to take into account of time. It's pretty good stuff, right? Pretty high level stuff. And the Amazon has the advantage that it can get these amazing results because it has hundreds or thousands of really clever data scientists all working in very mature teams trying to do it, right? And that up until now has been the case. So how are you gonna code one of these things, even if you have TensorFlow and all that? How are you going to code one, particularly at scale? Okay. Well, here's the exciting bit. This is my last slide, right? I got about a minute and a half to go. You're probably pretty relieved. I'm going to introduce you to TigerGraph Machine Learning Workbench because in order to run a graph neural network, you need a graph. And of course, a graph database is a really cool place to encode that, right? A really great place to encode that. But the cool thing about TigerGraph Machine Learning Workbench is it connects your graph database, TigerGraph, through to whatever your favorite machine learning framework is and environment is, right? So if you're on Google, Vertex AI, maybe with TensorFlow. If you're on AWS, you've got SageMaker, Microsoft Azure ML on Azure. It gives you access to whatever your pre-learned models are, but it allows them to work as if they were originally encoded with a native graph backend, right? So it allows Vertex AI to think and use TensorFlow or PyTorch or whatever it is you're using, right? It allows you to do that as if it were always built on that. and it allows you to interact with TigerGraph through Python on a Jupyter notebook. So I got 10 seconds left. Thank you very much for your time. If you're interested, you can get a free TigerGraph Cloud instance on tigergraph.com/cloud, or you can contact me to arrange a demonstration at sales@tigergraph.com. Thank you very much for your time.